Given, a string S containing only digits. Rule, digits map from 1 to 26 into letters, and 0 must be paired in 10 or 20. Return, the number of possible decodings of S. In the first example, one split is 1 then 2, which maps to AB. Another split is 12, which maps to L. So there are two valid decodings. In the second example, the valid groups are 2 2 6, 22 then 6, and 2 then 26. That gives 3 decodings. Example 3 is 0 6. Because a leading 0 cannot be decoded by itself, there are 0 valid decodings. Start on 1 2 6. From the first position, 1-digit and 2-digit choices are both valid, so the path forks. If you took 1 first, the remaining prefix can choose 2 or 26. If you took 12 first, only 6 remains. The final answer is just the number of valid branches that reach the end. Now see why branches can die. In 306, trying 30 fails because pairs above 26 are invalid. A standalone 0 also fails because 0 has no letter by itself. So any path violating these rules contributes 0 ways. With a string like 1212, different branch histories can land on the same remaining suffix. Here the question ways of 12 appears more than once. Instead of recomputing it every time, store that answer and reuse it. That reuse is the dynamic programming win. For 111, you can take 1 digit first and leave 11, or take 2 digits first and leave 1. So the count adds 2 subcounts, which is the Fibonacci-style recurrence. The only adjustment is validation. When a 2-digit pair is invalid, that branch contributes 0. Start with the idea, not the slickest implementation. The recursion tree labels each call by the remaining suffix string. Edges show the 1 or 2-digit chunk you consume next. On the side, memo caches answers keyed by that whole substring, so repeated suffix questions reuse work. When the remaining string is empty, you finished one valid decoding, so that leaf returns 1 to its parent. If the remainder begins with 0 in an invalid way, that branch returns 0, we only flag that rule here. Memo stores one entry for the empty suffix with value 1. Both 6 nodes share the same substring key, so memo of 6 is 1. Then 26 yields 2 ways, and the full string 226 yields 3. We keyed memo by whole suffix strings for clarity. In real code the input S stays fixed, so each suffix is really one start index I, store the same counts in memo at I, empty suffix is I equals N, same answers, but keys are small integers 0 through N instead of copying tails into the map. Quick example 102. If you peel a single 1, the rest begins with 02, which is invalid as a fresh letter code, so that branch contributes 0. If you peel 10 as one letter, you are left with 2, which finishes in one way. So the total is 1. Let n be the string length. Time is linear, order n, because memoization ensures each index is solved once and each solve does constant local checks. Space is order n for the memo table, and recursion stack depth is also order n in the worst case. A bottom-up variant also uses linear space, or constant rolling space with careful state compression. Define the main routine decode ways on string S. Get n as the string length. Initialize memo to cache answers by index. Define helper solve of I. If I reached n, that branch formed one complete decoding. If the current digit is 0, this branch is invalid and contributes 0. If index I is already in memo, return the cached result immediately. Always try the one-digit move solve I plus 1. Only if the next two digits form 10 through 26, the two-digit move is valid. When valid, add solve I plus 2 into the same result. Cache this index result in memo. Return the computed result for solve of I. Final answer is solve at index 0.